Standard biological models often depict fertilization as a massive linear race. Millions of sperm cells are dropped at a starting line, sprinting toward the ovum as they follow a simple path of localized chemical cues. Physically, this mass competition model is completely impossible. Localized chemical gradients cannot span the macroscopic distances of the cervix and uterus to guide a cell toward its target. On their path to the egg, these microswimmers encounter a sequence of physical barriers, from outward-directed mucus counterflows to fluids with high dynamic viscosities. Successful fertilization requires a regulated two-part gauntlet. First, a physical process of fluid mechanical rectification, and finally, a localized chemical filter. Instead, long-distance navigation is governed entirely by rheotaxis. This is the mechanism by which microswimmers orient and move against a fluid flow, rather than swimming in a random or chaotic distribution. This micrograph tracks a single bull sperm through a microfluidic channel. Instead of a straight line, it follows a specific upstream spiraling trajectory. By spiraling along the boundaries, they sweep the oviduct surface, massively increasing the probability of intersecting with the egg. Traditional biological models fail to account for these results because they overlook the microscale fluid dynamics that dictate the cell's physical path. The macroscopic environment of the reproductive tract is characterized by outward-directed mucus flows and dynamic viscosities reaching 20 millipascal-seconds, roughly 10 times the viscosity of water. In these environments, sperm cells exhibit boundary accumulation. Instead of swimming through the fluid's center, they become physically trapped against the walls of the cervix and uterus. Trapping results from hydrodynamics. The flagellar beat traces a conical envelope. Upon collision, it aligns with the wall, forcing the propulsion vector into the boundary. Locked in a two-dimensional plane, cells slide along the surface layer, unable to return to the channel's open center. By restricting cells to the wall, the reproductive tract forces them into the steepest part of the shear flow gradient, which is the prerequisite for rheotactic navigation. Fluid moving through the reproductive tract follows a Poisson shear flow profile. The velocity is zero at the channel wall and increases linearly with the distance from that boundary. This schematic represents that gradient with blue arrows. Because the cell is trapped at the wall, its tail experiences higher flow velocities than its head, creating a differential torque that mechanically rotates the cell upstream. However, simple upstream alignment only explains one-dimensional movement. It does not account for the transverse spiraling that allows the cells to sweep the tube's surface. Transverse movement is generated by the chirality, or handedness, of the flagellar beat. Mammalian sperm flagella do not just beat back and forth. Instead, they exhibit a complex three-dimensional helical rotation. We can see this helical nature in the geometry of human sperm. In low-viscosity environments, the flagellum displays a strong chiral beat component, appearing as a complex three-dimensional curve. Contrast that with bull sperm in the same fluid. Their flagellar beat is approximately planar, appearing as a straighter line. This reduced chirality results in significantly less transverse spiraling. These plots confirm the link between geometry and movement. Human sperm on the left show massive shear-induced transverse velocity, while the flatter bull sperm on the right show almost none. Upstream navigation depends on this geometric asymmetry. It is the interaction between the three-dimensional flagellar wave and the fluid boundary that enables the cell to stay on track. In vivo, these cells do not face a static environment. They are exposed to sudden temporal flow reversals driven by muscular contractions of the uterus. This tracking data shows the response to a flow reversal. In low-viscosity fluid, human sperm perform a sharp U-turn, realigning in 5 to 10 seconds. Viscosity dictates response speed. At 12 millipascal-seconds, the turn becomes wider and response time increases 5-fold. These graphs show that the cell's response can be predicted through simplified kinematic equations. By modeling shear alignment, chirality, and orientation noise, we can replicate the velocity curves seen in the tracking data. These reorientation times closely match the frequency of cervical contractions. This suggests the cells have evolved to utilize fluid mechanics, turning the hostile counterflow into a mechanism for efficient transport. Once rheotaxis guides a subpopulation into the fallopian tubes, the governing mechanism shifts. Macroscopic physics is replaced by microscopic chemical ecology. research into cryptic female choice shows that the ovum actively filters the incoming population of sperm cells. Follicular fluid surrounding the egg releases specific chemoattractants that act differentially on the incoming sperm. These chemical signals physically alter the sperm's movement. Based on the identity and compatibility of the male, the egg signals can cause a swimmer to straighten and accelerate, or cause its forward velocity to plummet. The egg exerts a post-mating gamete-mediated choice. It acts as a highly specific chemical filter, overriding earlier selection processes to determine which cell will fertilize it. The journey to conception consists of two distinct layers of selection: the macroscopic physical gauntlet, governed by morphology and rheotaxis, and the microscopic chemical filter of gamete-mediated choice. While motility is essential for movement, it is insufficient on its own. A cell's success depends as much on its specific geometric response to flow and its chemical compatibility as it does on its swimming power. These biomechanical variables and chemical incompatibilities provide a new framework for specialists to identify specific causes for cases of previously unexplained infertility. This data also provides a direct pathway for optimizing the viscosity and chemical composition of artificial insemination media to better support sperm navigation. At the microscale, life is the result of a mathematically precise interplay between fluid dynamics and chemical ecology.